Okay, so in this online lecture I'm going to be talking to you about temperature in paramagnetic systems. So we'll be mostly working with the idealized two-state model of a paramagnet and talking about some of the odd types of odd temperatures that can arise in this system. So you can get infinite temperatures and negative temperatures as well as positive temperatures. Before we get into the paramagnetic system, I'm just going to have you recall temperature and how it's related to entropy and energy and ideal gas and the Einstein solid. Okay, but the topic of today, this lecture, is temperature in paramagnetic systems. But before we get into the paramagnetic system, we're going to review or recall how temperature is related to entropy and energy in ideal gases and Einstein solids. So first recall that for an ideal gas, we can estimate the entropy using the Sackur tetrode equation. So this is nk natural log of V over n 4 pi m u 3n h squared to the 3 halves, and then let's see, I think this is plus 5 halves, if I'm not mistaken. Okay, so this is the Sackur tetrode equation for relating entropy to various quantities of an ideal gas. So the quantity we're interested in here is the energy, because of course the temperature of a system can be defined, and that's what we're going to be talking about a lot today, or in this lecture. The entropy, the derivative of entropy with respect to energy tells us about the temperature in this way. So how does S depend on U here? So we have S is proportional to log of U, U to the 3 halves power, but of course log of something to a power, the power can always be brought out of the logarithm. So here we'll say that S is depends on U in the as log U, roughly. So there's more to this dependence, but the U dependence itself is just log U. Okay, so how about for the Einstein solid? For the Einstein solid, we also came up with an approximate entropy that is in the case where n is large and where the energy Q is also large compared to 1, then in that situation the entropy of an Einstein solid is approximated by this expression. So remember, this case was for n being large and for energy being not too small as well. Similarly here, n has to be large and Q has to be large as well. But just recall, this Q here is related to the energy. So the energy of this Einstein solid is Q times some constants h in some f naught. So Q is directly proportional to U, and therefore for this Einstein solid we also have the situation where the entropy goes like log U, right? So in both the ideal gas and the Einstein solid, entropy increases with U as log U. So what does that look like? Let's draw a sketch of how S depends on U. And so basically I'm just drawing an approximate log function here. So this is a logarithmic rise of S versus U, so this function is log of U. And what I really want to point out here is that the temperature of both of these systems, right, the temperature is related to the slope of this function, right? ds du is the slope of this curve. And what we can see and what we know about a logarithmic function is that the slope, that is ds du, is always greater than 0. This is a monotonically increasing function, so the slope is always greater than 0. Therefore, temperature is always greater than 0. Therefore, T must be greater than 0 for any energy in this system. So, in these systems, that is the ideal gas and the Einstein solid, it doesn't make any sense to talk about a negative temperature. It doesn't exist. Okay. Now we're going to contrast that with what happens in a paramagnetic system next. So I'm going to erase this and we'll start considering a similar argument, but now looking at the paramagnetic two-state system. Okay, so in this case, let's see, let's write down an expression for the entropy. So for the two-state system, we found that the entropy, at least in the high n, so the limit where there's a large number of dipoles and that the number of them pointing up or pointing down is also large compared to 1, then we came up with this approximation. So we have n log n minus n up log n up minus all right. So this is an expression we came up with recently by applying the Stirling approximation to the log of multiplicity for a two-state system. Okay, and furthermore, recall that n up is n and n up are both related to the energy of the system. Remember, energy is mu times b times, this is one way to write it anyway, 2 and up. This is one way to write down the total energy of a two-state system. So the combination of these two facts, this s and this u, so the n up is related here. So it's not obvious what the shape of the s versus u function is by just looking at these two expressions, but we can think about it a little bit and get an idea for what this function looks like. How does s depend on u? So first of all, we can notice that unlike the ideal gas and the Einstein solid, there's an upper bound for the energy, right? The energy, this expression, the highest that it can possibly be is mu bn, right? If n up is equal to 0, and basically all of the dipoles are pointing down, anti-aligned with the magnetic field, then the highest energy that's possible in this system, so we could sort of cut that arrow off, this is the maximum energy possible, is going to be mu bn. So this axis is u, this axis is entropy. And similarly, there's a minimum possible energy, and that corresponds to the case where n up is equal to n, right? All of the dipoles aligned with the magnetic field. In that case, we have minus mu bn. That's the lowest possible energy of this system with n spins. Now, what is the entropy at these extremes? Well, at this extreme, like I said, we have all dipoles are aligned with the magnetic field. So n up equals n, and n down equals 0. And on this side, at this extreme, we have all dipoles anti-aligned. With the applied field. And likewise, that means n down equals n, and n up equals 0. Okay, so what is the entropy in these extreme cases? So if you recall your formulas for computing the multiplicity, or actually you don't need to even think about the formulas, you can just see right away there's only one way for all of the dipoles to point down and none of them to point up, right? So this is a case where multiplicity equals 1 at this extreme, and therefore entropy is equal to 0 at this extreme. And this extreme is the same. It has entropy. It has a multiplicity of 1. There's only one way that all the dipoles can point up, and the entropy is also 0 at this extreme. So we have 0 entropy here, 0 entropy there, and somewhere in the middle we have the maximum possible entropy, and that occurs at 0 energy. That is, that occurs when exactly half of the dipoles point up and half point down. That's what happens in this middle case, and this is the highest possible entropy. So this curve then has a shape that's like this, where the peak is at 0 energy. And now you can immediately see, if you start thinking about temperature for this curve, remember temperature is the slope, is related to the slope of this curve. So anything on this side, so at 0, well, what happens at 0 first? We could ask that question first. When the energy is 0, the derivative of this curve, the slope of this curve is 0. So at this particular point, so ds du equals 0. Therefore, the temperature, which is the inverse of ds du, that's 1 over 0, is infinity, right? So we're already seeing some of the oddities of what temperature can be in this two-state system. But by definition, the temperature is infinite at this point where the energy is 0. Okay, now on the left side of this curve, the slope is positive. So over here, ds du is greater than 0 and t is greater than 0. This is more like an understandable situation. Okay, but you can see now that on this side of the for the energy being positive, greater than 0, between 0 and mu dn, then this ds du is less than 0. Therefore, temperature is less than 0. Right? So you can see then that in this two-state system, you have some very odd situations where you can have negative temperatures and even infinite temperatures. And let's see, let's make a sketch over here. What does temperature as a function of energy look like? So you might recall from the ideal gas and the Einstein solid that temperature and energy are very simply related via the equipartition theorem. So that's not applicable here. Here, the relationship between temperature and energy is very odd. That is, as you start increasing energy, you have an increase in temperature that then diverges. All right, the temperature goes to infinity as it approaches this 0 energy. Likewise, you have negative temperature for positive U, and it also approaches infinity, and it does so in the following way. It diverges to minus infinity. Right? So temperature as a function of energy has this very odd functional form. It goes to infinity and minus infinity from the opposite sides here. Okay, so now let's take a minute to try to understand physically what does this mean. Is this just some artifact? Is this a bad theory? What does it mean physically? Okay, so first of all, let's just think for a moment about what it means for a system to be able to change its energy, right? So if you had a two-state system that was closed and not able to exchange energy with any other system or with its environment, then the energy in fact can't change, right? So you would be fixed at some particular level, and it would not be able to go this way or that way. So if it's a closed system, the energy doesn't change at all. Now, if it's not a closed system, as is the case for real paramagnets, right? Real paramagnets have magnetic properties that are represented by the two-state system, and more normal material properties that are maybe represented by an Einstein solid, for instance, if it's a solid paramagnet, or other things if it's a liquid. But the point is, for real paramagnets, you have energy exchange between the magnetic system and the vibrational degrees of freedom of the solid, for instance. And in that case, then the energy can change, and it will change depending on the temperature of the other part of the system, that is, say, the Einstein solid part of the system. That will determine where it will stay along this axis. But let's just think about this for a second. So if this system is able to give up energy, right, able to give energy to some other system it's in contact with, then it will indeed try to give up all of its energy. That is, it will try to give up all of its magnetic potential energy until all of its dipoles are aligned with the magnetic field. Right? This is potential energy, magnetic potential energy we're talking about here. So it's like pushing a ball up a hill. As you push the system in this direction, it gains potential energy. The ball rolls down the hill, it goes back to this low energy situation. So the magnet wants to have all of its dipoles aligned with the magnetic field. It wants to give up as much energy as possible and reach this lowest energy state. So, and it will do that. It will give up energy to its to the systems it's in contact with. But there's also energy that goes the other way. That is, the system that's in contact with can also give energy to this system and push its energy upward. And how does that happen? You should think of it as some sort of thermal agitation of the dipoles. So some temperature fluctuations will cause some of the dipoles to just flip randomly. And that random flipping is going to push you away from this extreme at this end and push you up to higher energies and therefore higher temperatures as you go along this axis. Right? So the exchange of energy between the magnetic system and some other system it's in contact with can push the system to an energy that's not at this low extreme that it wants to be at. Okay, but how does it ever get over here? Can it ever get over here? So not by just thermal exchange with some environment. So by thermal exchange with an environment, at most it could get to something like zero energy, where if you had a very high temperature system, it would be kicking and agitating the dipoles so vigorously that they would be sort of randomly aligned, some of them up, some of them down. And in that case, if you've got random alignment, on average it's going to be this situation where the energy is zero, where half of them are pointing up or half pointing down. Such random agitation is never going to put you in this situation where all of the dipoles are anti-aligned with the B, or at least exceedingly rarely. So how do you ever get to a negative temperature situation? Well, one way to do it is to actually reverse the B, right? If you take the applied field and suddenly flip its direction to opposite what it was, then this sign changes and this sign changes, and suddenly you have, so if you started with a system that's, say, here, and you suddenly flip the sign of B, then your system will all of a sudden be over here on this plot in the negative temperature territory. And there are experimental, there are experiments in which that's been done. You can actually flip the magnetic field fast enough that the dipoles don't have time to keep up with the flip, and for a short period of time, while they're all flipping back to try to align themselves again with the magnetic field, the system is giving up a lot of energy as it does that. Okay, so that's the situation, and that's where you can get these odd infinite and negative temperatures. It does have physical meaning, and it's something that's unique to these, or certainly it only occurs in the two-state systems, and what compared to the Einstein model in the ideal gas where it does not happen. Okay.